Welcome to ECE CS 552, lecture on integer dividers. In this lecture, we'll discuss integer division in two different forms, both restoring and non-restoring. These are not crucial topics for the project as you will not be implementing division in your processor that you're designing. We'll start our discussion of integer division by reminding you of how you did long division back in third grade. So just as a simple example, if you take the number 74 and decimal divide it by 8, you expect a quotient of 9 with a remainder of 2. The way we do this in binary numbers is very similar. So again, we express the numbers in binary. We copy the dividend and the divisor into the diagram as shown here, and then we proceed to iteratively subtract the divisor out of the dividend, and if we succeed, then we put a 1 into the quotient. If we fail, we put a 0. So we sort of skipped over the first 3 bit positions here until we get to the point where we successfully can subtract that out. Then we start copying again additional digits from the dividend down to the remainder until we get to the point where again we can successfully subtract the divisor out. For that bit position, then we put a 1 into the quotient, and then what we're left with at that point is the remainder. There are no more bits to copy or no more digits to copy down from the dividend, so at that point we're done. And you can see that we got the expected result. The quotient shown at the top is a binary 9, and the remainder shown at the bottom is a binary 2. So how do we map this to hardware? How does the hardware know if the division will fit as it does those checks? Well, the condition that we're looking for is if the remainder ends up being greater than or equal to the divisor, then we can then we know that it fits. To perform this check, we'll use subtraction. We'll simply subtract the divisor from the current remainder, and as long as the result is greater than or equal to 0, then we know that it fits. And when it does fit, what do? Well, we compute the next remainder, and that's just the current remainder minus the divisor, leaves us with the remainder for the following step. If it doesn't fit, we basically now have to restore the original remainder because remember we subtracted the divisor out of it, so we've changed the value. We have to put it back to the way it was, and this algorithm is called restoring division. Here's a flow chart that walks us through the process for integer division. Just for your reference, I'm leaving the example from the earlier slide in the bottom right here. So the first thing that we do when we do integer division is we test the remainder. We test to see if it's greater than or equal to 0 or less than 0. And depending on that test, we will either just shift the quotient register to the left and set the new rightmost bit to a 1. In that case, we knew that the divisor fit into the remainder, or the right-hand path to be we restore the original value and then move on. In step 3, we will shift the divisor register right 1 bit. Then we'll check to see if we're done, meaning have we done all of the repetitions? If not, we continue. If we're done, then we're done. We've computed the final result. Here's what the data path would look like for this simple integer algorithm. Once again, we have a divisor register that we load with the divisor value. We have a quotient register that we put the quotient into, and then we iterate through this data path by using a 64-bit ALU, again, to subtract the divisor from the current value of the remainder. And if it fits, then we continue. If not, then we keep shifting and restore and shift and go to the next iteration. There's a few straightforward improvements that we can apply to this simple divider. First of all, we can skip the first subtract because we know we can't shift a 1 into the quotient in that case anyway. So we'll shift first, then do the subtraction, and then finally when we're all done at the end, we'll undo the extra shift. The hardware ends up looking remarkably similar to the multiplier, and a good strategy for a low-cost implementation that does both multiplication and division would be to share the data path hardware for both cases. Here's what the revised flowchart looks like for the improved divider. It's very similar to the earlier one. I'm not going to walk through this in detail. I'll leave that as an exercise for you, the listener. And here's the data path. Once again, it's somewhat simpler than the initial version, and again looks remarkably similar to the multiplier hardware, except that of course the control logic is going to be a bit different in this case, and it's going to take still twice as many cycles as there are bits to complete, because every time we realize that the divisor does not fit into the remainder, we have to still undo the effects of that subtraction. That observation triggers yet another improvement to this design. Like I was saying, the division will take 2 cycles because we have to do these 2 conditional steps, subtract, and depending on the value of the result of the subtraction, we either restore or don't if needed. We can reduce this down to 1 cycle per bit by employing an algorithm called non-restoring division. And in non-restoring division, we actually will avoid the whole restore process, as you might have guessed from the name, when the test fails. The mathematical basis for non-restoring division is shown on this slide. So if we think about the remainder that needs to be restored at a particular step I, r sub I is defined as r sub I minus 1, so the remainder from the previous step minus the divisor d. If that's negative, then we have to restore. That's the way we explain things in the earlier versions of the division algorithm. But if we do a little bit of algebra, we can actually show that we can do something a little bit more intelligent than that. If we think about what happens in the next step, I plus 1, the value r sub I plus 1, which is the remainder in the next step, is going to be the remainder from the time step I, r sub I, shifted left once, so that's the same as multiplying it by 2, and then subtracting the divisor from it. Well, if we rearrange the terms a little bit and rewrite this, we see that that's actually 2 times r sub I minus d plus d. Now realize that after the failed check in the previous time step, the exact value that we had was r sub I minus d. So rather than restoring that and then shifting it, we'll simply take that non-restored value, we'll shift it, and then instead of subtracting, we'll add. And mathematically, we'll get an equivalent remainder for the next time step when we do that. So again, just restating, we can recompute r sub I plus 1, not by restoring r sub I and then computing it the usual way, but instead we add instead of subtracting d. And that'll give us the correct remainder for the following step, and now we can complete this process with a throughput of 1 bit per cycle. So for a 32-bit division, we can do it in just 32 cycles. Here's a detailed example that shows how non-restoring division works. You can see here that the number we're starting with is 7, so we preload that into the remainder register. We're dividing by 2, so we already know what to expect as far as the result goes. We would expect 3 and then a remainder of 1. So if you go through each of the steps in this slide, again, we're simply implementing the algorithm that we already discussed step by step. What you end up seeing then is that at the end of this, we in fact are left with a 4-bit remainder on the left-hand side of the remainder register, and a 4-bit quotient, which is 1, 1, or which in binary is of course the value 3. So we ended up with the correct result. Summarizing this lecture, we covered 2 different types of integer dividers, a multi-cycle restoring and a multi-cycle non-restoring. There are other more aggressive approaches for division. One of them is called SRT, named after its inventors, Sweeney, Robertson, and Toker, which uses lookup tables to perform some of the steps in the division. There's a very famous bug that was in one of the Intel processors in the early 1990s that affected the floating point division hardware in that processor that actually was using this SRT algorithm, or a variant of this SRT algorithm, and they ultimately figured out that the lookup tables that they had included in the design were incomplete. There were a few entries missing, which led to the divider generating the wrong results for very specific operand values. Other methods that are used for high-speed dividers are based on a Newton-Raphson iterative method, and the basic idea with the Newton-Raphson method, which you may remember from some of your math classes, is essentially to first estimate the reciprocal of the divisor, and then iterate to refine that reciprocal until finally you've reached full precision, and then simply multiply by the reciprocal rather than trying to do the division directly. So this is a technique that is widely used in high performance dividers today. These kinds of techniques are well beyond the scope of this course. We really only expect you to understand the operation of the two multi-cycle dividers mentioned above.